Hi everyone, I'm going to talk about work that I have done in Nottingham during a laser gun exchange there. We used data from the 300 project, which has a set of 324 resimulations of galaxy clusters environment with full physics that were identified in the multi-dark simulation. We identified the filaments with dispersed, and we studied their properties. This is a particular population of filaments because they live in very high density regions. They are associated with very massive galaxy clusters, and they are in general short compared to the traditional very long filaments that we can find in the literature. If we can study the density profiles, the velocity flows around these structures. For example, with the density profiles, I have a plot here. This is the distance to the filament axis, and this is the density. We can see that they show a core near the spine of the filament, and in the outskirts of the filament, the profile decays with a power law with a slope ranging between -2 to -3. So depending on the position along the filament, the profile varies. For example, the node near the node, the density tends to be higher, and the slope changes to -3. This is in general the case for gas, dark matter, and also galaxies. So we see the core and the power law. For the case of the velocity flows around the filaments, in general they are very complicated, but the trend is that the material tends to fall to the filament, and at the same time it flows towards the nodes. Here I have an example of one of the galaxy clusters that were resimulated. This is the gas, and we can see that the main halo is located exactly at the center, and we see the detected, the identified filaments with dispersed in white, and this software also detects saddle point nodes and other points. We can see that there's a very strong spherical symmetry, and the filaments are very radial. So this is going to be a problem because these are not randomly orientated, so it is difficult to account for the influence of the main cluster. So we have to be very careful to in order to disentangle the properties from the filament themselves from the properties of the halo. So here I have a diagram of a filament. Here you see a filament, 3 filaments detected, and for us, a filament goes from a node to the saddle point. So a traditional filament will go from a node to another node, but for us, it stops at the saddle point because this is the region of influence of this node. So the material that falls into the green part is going to account for this filament, and it's going to be governed by this node. If you go beyond the saddle point, you're going to fall in another filament with another node. So everything that falls into the green region, for example, is going to account for this filament. And the properties that we use, the quantities that we define in order to study these structures are the distance to the filament, which is shown here, and also the distance along the filament from the node, normalized by R200. So this is a measure of how close it is to the node. And another thing that is important in this work is that we are only interested in the diffuse material in the filaments. These objects tend to be populated by many clamps and halos that have their own properties and own density profiles, and we consider them to be contaminants. So we have to remove these regions by removing all the particles that fall into these spheres. We use time handler to remove. Here I have an example of a filament, the gas and the dark matter counterpart. This is the identified filament by disperse, and here it is without removing anything. So we can see that there are many clamps and very small halos. But if we remove one time R200, we can see that the very high density peaks are removed, but you can see the remaining material around the halos, like these shells that you can see here. And if we remove 2 times R200, we see that all the material associated with halos is largely removed. But if we remove 3 times R200, we're going to be left with almost no particles, and yeah, this is not good for the signal quality. In order to account the effect of the galaxy cluster or the distance to the galaxy cluster, we have to randomize the network in order to be able to estimate the signal associated with the proximity to the galaxy cluster rather than the proximity to the filament. This is the case. In this case, we have the gas phase diagram. So this is the density, and this is the temperature. If we don't remove anything, we have the complete phase diagram of the gas. And as soon as we are removing material around the halos, we see that the very dense and hot material associated with the halos is being removed, and it's only the diffuse gas is left. Here I have the density profiles for 3 populations of filaments divided by classified by the size of the associated node. So all the filaments that have a small node are going to fall in, are going to be contributed to this signal, and this is for medium-sized nodes, and this is for big nodes. All the big nodes are normally the center of the galaxy cluster. So we see that in general, we see a core profile near the axis. So this is in agreement with other works, and also a power law decay at the outskirts of the filaments. We also see that this is the gas and this is the dark matter. We see that near the node, so it varies, and it is a much higher density. The density is much higher near the node compared to very far from the node. And we can see that also the width of the filament also changes between the different populations. And if we calculate the gas fraction, we can see that the gas fraction tends to increase towards the axis of the filament. And for the small nodes and medium nodes, we're going to see at the same, more or less the same trends. But for the big nodes, we see a bump in the gas fraction that we think has to do with the presence of a shock of the gas around the center of the galaxy cluster. If we look at the velocities, in this plot, we have the distance to the filament axis, and this is the input velocity. So we can see that in the outskirts of the filaments, the velocities are negative, so it means that the material is collapsing to these structures, and it tends to go to 0 when at the center of the filament. We see that for gas and dark matter, the trend is similar, but they have differences. Dark matter has a wider distribution of the velocities. This is because the gas feels the pressure, whereas the dark matter doesn't feel any pressure and is free to reach a wider range of velocities. If we look at the velocity fields, we see here I have the distance to the filament axis and the position along the filament. So for this plot, for example, the node would be around this position. So we see that the material tends to flow towards the filament, and at the same time it goes towards the nodes. And for dark matter and gas, we see that in general they have the same behavior, but if we look closely, we can see that here, for example, between 2 and 3 megaparsecs, the gas has a positive velocity of the parallel component. So it means that the gas is going away from the node in these positions. And here we have much negative velocity, so it is funneling towards the cluster. So we can also see this in these plots. If we color code by the gas fraction, we see these plots, and the lines represent the velocity component that is parallel to the filament. So for small and medium filaments, we see that it tends to be negative, so the material goes towards the nodes. But for big filaments, those that are associated with the center of the galaxy cluster, we see much violent velocity flows. We see that at the center of the filament, the velocities tend to be very negative, so it goes very fast towards the cluster, the center of the cluster. But here, between 2 and 3 megaparsecs, we see the bump in the gas fraction that we have seen in the other plots, and we can see that also the velocities are positive, so it means that the gas is flowing away from the node. So for the gas, this happens, but for the dark matter, it doesn't happen. So it is like there's a vortex with the gas case, and it means that the gas tends to be flowing more efficiently through the filament and is being injected towards the. It is injected in the galaxy cluster very efficiently through the filament, but outside the filament, it is going outwards. It is like the gas is able to penetrate the gas shell, the gas choke efficiently through the filament, but it is not the case for dark matter. Here we can also see the same story, but in a different point of view. If we look at the input velocity towards the center of the cluster and separate by particles inside filaments and particles outside filaments, we have the dark matter on the left and the gas on the right, and at different distances, ranges of distances from the galaxy's cluster center. And we see that it doesn't matter whether we are inside a filament or outside a filament for the dark matter case. It is the same. You are going to fall towards the center of the galaxy cluster the same way. But for the gas, this is a completely different story. It really matters whether you are inside a filament or outside a filament. If you are inside, the velocities are going to be much negative. So it means that it is very efficient for the material to be injected through a filament to the center of the cluster. So this is important. And in general, we see that an agreement with other works in regards to the density profiles. We see a core and a power law decay. We see that different populations of filaments have different properties. The filaments that are associated with big nodes tend to be thicker, and the gas fraction tends to increase towards the filament spine. But we are not very sure about this because the filaments were identified with dispersed with the gas. So it could be a bias. And we also see that the velocity dispersion is different for either gas and dark matter. And we also see a vortex that is present for the gas, but it is not present for the dark matter. And yeah, and that the gas is being accreted more efficiently through a filament. So this is all. Thank you.